Right. This is the day 3 of elasticity. So far we have covered all the theory parts and did some questions as well regarding elasticity. So today I'll be mainly focused on doing more questions to enhance further your knowledge. So you have essay questions at the back of the tute. Please turn to that essay questions and try the first essay question. Right? I'll give you some time to try the essay question. First essay question. Okay. Length of a wire is 2.5 meters. You can draw a sketch. And cross-sectional area of the wire is -3 square centimeters. You have to convert this into square meters, right? So multiply by 10 to the power -4 square meters. When a load 0.4 kilogram, that is 4 Newton, is applied, extension of the wire is given as 1 millimeter. It is given as 1 millimeter. So you just so what they ask is you to find the Young's modulus, right? So you just have to do a substitution. This is a simple question. So Young's modulus is equal to FL divided by AE. So you just have to substitute values here. So the force that string is submitted to is 4 Newton. Length is 2.5 meters. Cross section 10 to the power -3 -4, so it is -7 square meters. Extension is 1 millimeter. When you convert it into meters, it becomes 10 to the power -3 meters. Okay. So 4 times 2.5. Force of 2.5 is 1, right? Sorry, 10. Here you have a 10, -10. When it goes up, it becomes +10. So the value is 10 to the power 11 newtons per square meter. So that is the Young's modulus of this material that is used to make this wire. So that is copper, they say, right? That is copper. So I gave you this question just to remind you the equation, right? Just to remind you the equation. Right. Then try 23rd question. 23rd question MCQ, right? 23rd MCQ. Out of two wires that are made of same material, so same Young's modulus, one wire has twice the diameter of another wire. Maximum load that can be applied to second wire is X times the load that can be applied to first wire. So let's say this is the first wire, this is the second wire. So let's say this is applied to a W load and the second wire is applied to a XW force, X times W, right? Another one is here diameter is D, here the diameter is 2D. And they are made of the same material, meaning they have the same Young's modulus. They have the same Young's modulus. Right. So that is all the data we've been given. So here what they ask is what is the maximum load that can be applied to this second wire without breaking it, right? So in the theory we discussed this. You can check that F break is equal to cross section times stress break. So this stress is only dependent on the type of material. Type of material. Since the type of material is the same, here you don't have to think about sigma break, right? So in that case, we can say F break is proportional to cross section of the wire. This is not dependent on the length of the wire, right? That's why they haven't given any length to this wire. Regardless of the length of each wire, F break is proportional to A. If you remember, this sigma break is only dependent on the type of material. Gave you on the notes, right? Right. So F is proportional to A. So let's say cross section of this wire is A. So A means 5d squared over 4, right? If you find the cross section of this, that is 5d squared over 4. Then if you find the cross section here, that cross section is 2d squared over 4. So these two, take 5d squared over 4 from here. Then in front of it, what you get is this 2 gets squared and comes as 4. So you can see when you compare these two, the cross section of the wire here is 4 times the cross section of the first wire. So if this is cross section is A, here the cross section is 4A, right? Since F brake is proportional to A, if the maximum force that can be applied here is F, here maximum force should be 4F. It should be 4 times, right? If area is 4 times, cross section is 4 times for the second wire, force required to brake also should be 4 times. That is what proportionality means, right? You can write this twice, then divide and find it, but it is not necessary, right? It is like a waste of time. If this is becomes 4 times, if brake also should be 4 times, should also be 4 times, right? So the answer there should be the fifth one, right? 4. X, the value of x is 4 there, right? So you have to remember this this one. F brake is equal to A times sigma stress at the breaking point of the wire. Okay, right, take it down. Right, then we'll try 24th question. In the question they say a string can bear a load of W without breaking. W without breaking. If the string is broken in half, so if this length is L, for the another string it is L over 2. What they ask is maximum load, let's say W dash, that can be held by this half of this string, right? Half of this string. So what is going to happen here? Again, remember this equation. F brake is equal to A times sigma brake, right? Do you see length of the wire here? What does this mean? If you don't see a variable for length of a wire, F brake is independent of length of the wire. Length of the wire does not matter to determine the force that it would break, right? So the here also, just because you take half of the string length, the maximum load that can be applied does not change. So here also it will be W. Okay, here also breaking load is going to be W. Let's say you get 1/3 of this wire, so L over 3 is still the maximum load that can be held by the wire is W. The meaning of that is F brake does not depend on length of the wire. Okay, because this equation, right? Okay, so the answer should be third one. Answer should be third one. Take it down. You can take your own notes, right? If you see a significant point, take your own notes, right? Even at the questions, right? Then we'll try 25th question. 25th question. When a mass is hanged from a spring, so a spring, its length increases by L. So the extension is L. When the spring is cut in half, So the same mass is applied, meaning same load. So what they ask is extension of half of the spring. Extension of half of the spring. Okay. So they're asking about is extension. They are asking about new extension for the half of the wire. Right. How do you find that? So if you remember this equation, right? F equals KE. This is for the springs, spring constant, and this is the extension of the spring. Then from Young's modulus, you can get this equation. When A goes to the other side, it becomes Y A divided by L E. So when you compare these two equations, what do you see? This K and this term should be same. So K is equal to what? Y A divided by L. Okay. So this is Y A divided by L. So according to this is going to be important. So K is equal to Y A divided by L, right? That is the combination between spring constant and Young's modulus, right? So it is the same wire, right? Sorry, same spring. Same spring means same material, but we have a half. So what we change is L, length. Get rid of cross section. Cross section is same for both springs. You don't need cross section and you don't need Y. So K changes with, I'll put a capital L, right? Because extension they have given as simple L. So total length of the here capital L, here length is L over 2. Right. So from this one you can, what can you see? So if you apply this proportionally to this one, let's say here the K is here the spring constant is K, let's say like that. So when you cut that in half, what happens? So this initial length becomes half. If it is half, when it goes to the numerator, it becomes 2. So this side is increased by 2 times. So the other side also should increase by 2 times. So if spring constant here is K and here spring constant should be 2K. If it is K, spring constant here should be 2K. See that spring constant changes, right? When you change the length of the cross section of a wire, spring constant changes, but Young's modulus does not. Young's modulus only dependent on the type of material. So when you get half of the length, spring constant doubled there, right? Okay, now we found the spring constants for each. So here, if we apply F equals KE to first spring, you get force is W, spring constant K, and extension E. Actually, extension is given as simple L, right? So use that, what they have given. Then again, for this one also, applied force is W, spring constant is 2K. Let's say, now the extension is E dash. Got it? Now you just have to, because both sides are same, I can say KL equals 2K E dash. KK cancels off, divide L by 2. So E dash. So the new extension going to be L over 2. This is L over 2. So the answer is third one. So if you didn't understand that, rewatch the question, right? These concepts you must get into your head, right? Clearly. So the new extension is going to be L over 2. The reason is due to, since this spring is cut in half, spring constant doubled. Got it? Spring constant doubled. Since the spring constant doubled, extension halved under the same load. That's what happened, right? So the answer should be third one for 25th. Right. Then we'll solve 26 as well. I'm solving all these questions because They have a key point there, right? Somehow you have to grasp that, right? Let's try 26. When a mass m is attached to a string with length L, it achieves proportional limit. So it achieves proportional limit. Remember this limit, right? Mass required to achieve the proportional limit if half of the wire is used. So now in this case they use a half of the wire. So what they ask is mass required. Let's say now the new mass is capital M. So you need to get capital M. So again, so in this case, when you apply this mass, this load, this gains the proportional limit. Okay, it gains the proportional limit for mg over A. A means the cross section of the wire. At a certain level, it gains that, right? So this is stress, this is strain. Then when you use half of the wire, remember this equation? F break equals cross section times sigma break. Proportional limit also is similar. It is a special limit, right? So, as I told you before, F break does not depend on length. By changing the length, you cannot change FB, break-in force. So here also load is going to be mg. So when you apply mg, this is going to reach proportional limit. By taking half of the wire, it is not going to change, right? So we'll have the same graph here, E over L. Here this is the stress. This point is very important, right? Try to understand this. Many students don't understand this, right? So as I told you before, this graph, stress strain graph, is dependent only on the type of material. This graph dependent. So these points only dependent on type of material. By changing the dimensions, these values do not change. These values do not change. Okay. So let's see what happens when you take half of the length. When you take half of the length, what happens? This cannot change, right? E over L cannot change. So what happens now? Now the length becomes half. To have the same E over L, what should happen to the extension now? Extension also should be halved. So this half cancels off. Then that point, when you take half of the wire, also would coincide on the graph, right? Again the value should be E over L. But if you take a FE graph, force extension graph, so the force is mg, that is the applied force mg. We didn't change stress, right? Then let's say this is for the length L wire. This graph is for the L wire, and the extension was simple E. So when you take half of the wire, what is the new extension? In order to keep this strain constant, extension now has to be half. So extension should be half. mg does not change. We are applying the same mg. So the new graph, FE graph, is going to be this one. Extension became half, right? And the length is L over 2. So you can keep the same value for E over L. Strain remains the same, but extension changes when you take half of the wire. So that is a key concept that you have to understand, right? Some like in essay questions, they have so far asked for like an essay question, I think 2009. You need this knowledge clearly to get the right answer there, right? Okay, you can draw both graphs. It is the same graph for L length and half of the length as well, right? Study this question carefully. Many students don't understand this, right? But if you try this one like twice, you will get what I'm saying. Here, strain remains the same. When you cut a wire, strain remains the same, but extension changes, right? Extension changes because strain needs to remain same, right? That's the reason. Right. Then let's try 27. First try the question, right? First try the question and send me the answer. Try the question, send me the answer. 27. Right. To increase the length of a wire by a unit extension, required force is K. So they are saying about spring constant, or you can say force constant. Actually force constant here, right? Because it's a wire. Consider the expressions about K. So if we remember the earlier case, K is equal to YA divided by length of the wire. YA divided by length of the wire. Initial length, right? Sentence A. By increasing the Young's modulus, value of K can be increased. So once you look at the question, sentence increase the Y, K increases, right? Because this is at the numerator. When increase Y, K increases. By increasing the cross-sectional area, K. So by increasing cross-sectional area also, we can increase K. Okay, that also is in numerator. Then by decreasing the length, K can be increased. Yes, by decreasing the length as well, K can be increased because this is at the denominator. When you increase, so at the denominator, properties have an inverse proportionality, right? With this one. So when decreasing L, what happens? K increases. So all are true. That's an easy question. If you know this, right? Right. Then try 28. I'll give you some time, try that. Right. 28. Force constant of a wire made of a material with Young's modulus Y is K. Okay. Force constant K, Young's modulus Y for the material. If the wire is cut in half. So what do we change here? Length of the wire, right? Length of the wire, we are making it a half. So what they ask is, sorry, this equation should be K equals, right? Not Y equals. Okay, K equals Y over L. So when length is halved, what happens? So this factor is halved. It is at the denominator. This half goes up. Then it becomes 2. If this side gets twice doubled, other side also should get doubled, right? So if something at the denominator is halved, this value should be doubled. Got it? So you should know these, like dealing with factors and proportionalities. You need to have a higher level practice on those, right? So what should be the answer? Young's modulus remains Y because material does not change. But the new spring constant doubled. Spring constants become 2K, right? If it is initially K, now it should be 2K. But the Young's modulus does not change because by cutting you cannot change the type of material. So the answer should be fourth one. Answer should be fourth one. Okay, now we have a similar question. Not a similar question, it is like the same question. 13th question, just try that, just to practice. 30. Okay, so the answer is 2K, right? This is I have to do the same explanation, so the answer is 2k. Okay, then try 44. I'll give you a minute. Try 44. Right. A and B are two steel wires. Diameter A and B, two steel wires. Both are steel, so Young's modulus same. Diameter, let's say D here, and for A it is twice. They say it is twice. And the length is thrice. So if this length is L, here the length is 3L. So I have to compare these two wires. When both wires are subjected to the same force separately, so let's say we apply same W, ratio between elastic potential energies is, right? Now they're asking about something like elastic potential energy. Before that, if the diameter is D, let's say cross section is capital A. If the diameter is twice, new cross section should be 4 times. Why? Cross section is 5D squared over 4, right? If D gets twice, if D gets doubled, that factor gets squared. So it comes out as 4. So this time gets 4. Cross section should be 4 times the initial value, right? Don't waste time writing too many equations to get that, right? You should be able to say that when the diameter is twice, cross section should be 4 times, right? If you don't, then you are going to consume a lot of time and just complain that you don't have enough time in the exam, right? It is not that you don't have enough time, it is you lack these skills, right? So here the cross section is A, here the cross section is 4A, because this gets squared, right? Hope you understood that. Right, so what they ask is ratio of elastic potential energy. Right. So for this case, so what is elastic potential energy? That is half Fe. If you don't remember, you can check from the notes. Half Fe, right? So for this one as well, I'm going to use a proportionality. So without proportionality, it is not possible to do MCQs, right? Right. So in both cases, W is the same, right? So you don't need W. Half is just a number. So from this one, what can you say? Energy is equal to extension. Not equal to, proportional to the extension of each wire. Right. So we need something for the extension. They haven't given extension directly in none of these. So what can we do? You need an equation for extension. So this is the fundamental equation. So the E is equal to FL divided by YA. Okay. So I need something for the extension. Since F is same for both, I'm getting rid of this F. I have to compare these two. F is same, right? Length changes, same material, get rid of Y. Cross section different. When you compare this is A, this is 4A. So now instead of E here, in this case they say extension is L over A. Then you can substitute it here. E is proportional to, you can say, length divided by cross section. Okay, now this proportionality is what we need, right? This is the proportionality we are going to use. Okay, let's say E1 is for the first wire, proportional to length. What is length? L. Cross section is A. Then I'll say E2, that is for the second wire. Length is 3L. Cross section is 4A. Okay. Then I'll divide E2 from E1. What do you get? L over A cancels off when you divide it. What is remaining is 3 over 4. This becomes just 1, right? So this is 3 over 4. So they are asking about the ratio. So the answer should be second one, right? So this question is going to be very hard if you just keep writing equations 2 times like that without writing proportionalities, right? You must use proportionalities. Don't be scared of using proportionalities, right? Be scared of using equations actually, because they are going to eat a lot of time, right? So somehow you need to develop that skill to using proportionalities. Okay, this is not that hard. So you are comparing these two. Just remove all the constants for both cases. Keep only the variables. Here the variables are length, cross section, length, cross section. All the other stuff, they are constants, right? So once you get rid of constants, you don't have to do unnecessary calculations and you can save a lot of time, right? So get used to using proportionalities, right? So without using this, it is not possible to do MCQs. Okay, right. Then let's try a 45th question. 45th, that also is involved with potential energy, I think. Try that first. Work required to increase the length of a metal by 1 millimeter is 2 joules. So extension is 1 millimeter. So the work required is 2 joules. Work required to extend another wire made of the same metal but with twice the radius. Here radius is R. For the another wire, radius is 2R. So what happens when radius is twice? What about the cross section? Cross section quadruples, right? Because cross section is 5R squared. If radius doubled, there's a factor 4 coming out of this. So it is increased by 4 times. So if the cross section here is A, cross section here is 4A. And the length is halved. Here if the length is L, for the another wire length is halved. But this extension, they say extension is same. So what they ask is, how much work do we need in this case? That is what they ask, right? So there are too many variables here, right? We have a length L wire with cross section A and another wire with half the length and 4 times the cross section. And we extend both wires by the same extension. So for this wire to have that extension, they say energy required is 2 joules. Then for the second wire, what they ask is what is the energy requirement. Okay, so that work done is stored as potential energy, elastic potential energy. So here as well, right? Here as well, just take equations like this. Let's say this is E potential energy, that is half Fe, half Fe. So what is common for both? I mean constant for both. Here the extension is same, here the extension is same. Get rid of extension to make it a. Then the energy is proportional to what? Energies in this case is proportional to capital F, right? That is the applied force. So in order to have the applied force, you are going to need those equations. Fa equals y E over L. So force is put A to the other side, y E L, there's a, right? I think the material, both are made of the same material, right? So you can get rid of y when you are comparing these two. Both have the same y. Get rid of y. Get rid of E. We have the same extension. Now the force is proportional to what? Cross section divided by length. Correct? Then instead of force here, you can put what? Cross section divided by length. Got it? Easy, right? Cross section divided by length. Okay. So for the first case, I'll write energy is 2, proportional to cross section is A, length is simple L. For the second case, that is what we need to find. Energy is E, cross section is 4A, length is L over 2. I'll further simplify this one. This 2 goes to the numerator and it multiplies with 4. So it becomes 8A divided by L. Got it? So this is the first proportionality. You can say this is the second proportionality. Then divide second one by first one. So at the left side you get E over 2 equals 8A over L divided by A over L. A over L cancels off. So E over 2 is equal to 8. Okay, E over 2 is equal to 8. So E is equal to what? 16 joules. 2 times 8, 16 joules. This case it is 16 joules, right? So this became somewhat easier, less complicated because we use proportionalities, right? That's why I'm telling you again and again, use proportionalities. Don't be afraid to use proportionalities, right? So the answer should be first one, that is 16 joules. Right, let's try 46. I'll give you a minute, try that. 46, okay, 46. Right, load of W is hanged by a rubber pipe, okay. Pipe means inside it is hollow. Inside is hollow, right? And its Young's modulus is E. Internal radius R1. So if you take a cross section, internal radius is R1, external radius is R2. So inside is hollow, right? Inside is hollow. So what do? We hang a W weight from end of this. So what they ask is an expression for when you, as a result of hanging W, what is the energy stored in this rubber pipe, right? Because this, it's extended by simply elastic potential energy is stored in this rubber pipe, right? So what they ask is, what is that? So what's the equation? Half force extension. Okay. So we know the force, that is W, right? That is the force submitted to the pipe. Force is W. Then what they ask is extension. To get the extension, we need this equation. Y E over L. So extension is FL divided by Y AY. Just remember one equation, right? Then from that you can get the equation you need. So extension is FL divided by AY. FL divided by AY. So we have this expression, but you have to relate this one to the question. Okay. So half W is in the question. Force, here the force also is W, right? So instead of F, you have to use W. Length, is it given length? Yeah, length, they say capital L. Now, let's say first I'll deal with Y. Capital Y, they have given it as capital E. For Young's modulus, sometimes we use capital E, right? Then we need cross section. So the only specialty about this question is cross section. For the cross section, you cannot use this hollow space. Actually, the cross section should be this one only. Okay. So how do we find this cross section? Cross section of the whole thing is phi r2 squared for the whole thing. Subtract that from the internal cross section, phi r1 squared, right? So this is the cross section of the solid space there. So now you can use that here, phi r2 squared minus r1 squared. I just took phi out, right? So W is squared L E, that's a phi r2 squared minus r1 squared. So what do we have? I think second one, right? Second one is what we need. Actually, I used, let's say this energy C dash, they are using E as Young's modulus, right? So I'll use E dash here for the energy, potential energy stored in the pipe. Okay. Potential energy is stored in the pipe. So the answer should be a second one, right? Take it down. Those who couldn't solve that, take it down. Right. Then let's try 50. I'll give you a minute. Try 50. So in the recording, you won't be given a minute, right, to try. So you can pause the video and try that question before I'm explaining the question, right? Take a minute and try that. In the recording, a minute won't be available, right? Okay, so the 50, a metal wire shows strain X. So what is strain? This value, right? Strain is what? Extension divided by length when a load is applied. Young's modulus is Y. Young's modulus is Y. So what they ask is elastic potential energy is stored in a unit volume. So let's say elastic potential energy is stored in a unit volume. What does it mean? Energy should be divided by volume of the wire. Volume of the wire. So what is energy? So if you remember, this is the property that you get from area of a stress strain curve, right? Stress strain curve. This is the property that you get. That's just to remind you the theory. Okay. Energy divided by volume per unit volume. Okay, so energy is half Fe divided by volume. Volume of a wire, cross section times length of the wire. That is the volume. So this is, you can arrange this as, you can divide A here, E here, and length here. So this is the energy per unit volume. Okay. Let's say that is, I'll give that a one term as capital E dash. Right. Then you just have to do substitutions and cross multiplying, then get the answer in terms of X and Y, right? Okay. I think we need to use this equation as well. F over A equals Y E over L. So F over A is equal to Y instead of E over L, I can use X. X is strain. So F over A is equal to YX. So half, instead of F over A, I can use YX. Then instead of E over L, what can we use? Again, X. Okay. So half Y X squared. So that is E dash. Half Y X squared. It is for E dash. Okay. So these are not hard questions if you know simple basic simplifications in O levels, right? So you just have to just put equations here and there, and then you can get the answer. But you need to know a small amount of theory as well, right? You should know what energy per unit volume means. Okay. So the answer should be yx squared divided by 2. The answer should be fourth one. Answer should be fourth one. Right? Take it down. Right, then try 51. 51. Try that and send me the answer in the chat box. 51. That is not a hard question. Right, so we've been given a graph, force here, extension here. The graph is like this, right? Graph is not linear. So so this is the graph when you extend a strip. It is a rubber strip, they say, right? So that is the extension is, they say, 0.5, and at that extension rubber strip gains 40 Newton. Required force is 40 Newton to give this amount of extension. 0.5 means that is in meters, right? So it is 50 centimeter extension, which are only possible in materials like rubber. So what they ask is, in this case, what is the energy stored? So how do you find the energy? Energy is what? Always remember area between extension axis and this one. Not this and graph, right? It is always graph and extension axis. The area between graph and extension axis. Remember that. Right. So but the thing is, we don't know how to find the area of this one, right? We cannot exactly find. We don't know how to do that. So you can find energy of this triangle and get an approximation. So what is the area of the triangle? This half. This length 0.5. 0.5 means half, right? I'll put another half. And the height is 40. This is 4. 40 means 10. So the area of this triangle is 10 joules. Area of the triangle is 10 joules. It is obviously area of this should be less than 10 joules. Okay. It should be less than 10 joules. So the answer should be first one. It is an easy question. It is an easy question. Right? You can take it down. So those who get the answer for that, try 52. Try 52. Next question. Right, so in the 52 as well, we have given a graph, FE graph. So for that one also, when extending a rubber strip, it follows this graph. As it contracts, it follows a different graph, right? It doesn't follow the same path. So what they ask is true sentences. Sentence A, after extending, strip does not gain its original position. So after extending and released, right? It should be included released. Extension again becomes 0. It follows a different path, but the extension becomes 0, right? So in that case, actually it gains the initial shape or the position. So A is true. B, work done when extending is more than the work done when contracting. So this is the work done when extending. That is the area. So this is the work done when contracting. Okay. So it is more. Work done when extending is more. B is true. C is heat can be produced in the process. So as you can see, there's a remaining area, right? This area. Actually, this area, what happens to that? So there's an energy loss there clearly, right? There's energy loss. So that mechanical energy loss. So that energy has to convert into something. The only thing that it can be converted into is heat, right? Usually that energy doesn't convert into like light, right? So practically that energy can be converted into heat. So that is the energy loss there. So this happens like rubber has a different, unlike metals, rubber has a different properties. I mean, different structure of molecular structure, right? That's why it follows something like this. This doesn't even have a proportional limit to anything like that, right? That's why rubber follows a graph like this, right? For this one, we cannot use Young's modulus and those stuff, right? Because this doesn't have a proportional limit. Rubber has its own force extension. Okay. Okay, so the answer should be all true for 15 to fifth one. Right, then try 54th question. 54th question. Give you a minute to try that. We discussed the theory on that already, right? So try 54th. Right, so we have an aluminium rod with length 10 centimeters. Aluminium rod, length 10 centimeter. I'll convert that into meters. So divide by 100. Cross-sectional area 20. 20 means if you convert it to meter squared, it becomes 10 to the power minus 4. Cross-section. Young's modulus 7 times 10 to the power 10. Then the linear expansivity alpha is 2.5 times 10 to the power minus 5 per Kelvin. So that is alpha. Alpha means linear expansivity, right? I have discussed those when we do theories. At 30 centigrade, it just slips. So this is between two walls. Then at 30 centigrade, this flips. But when it increases, when the temperature increases to 34 centigrades, what happens? This starts to get compressed, right? So the temperature increase is 4 degrees, 4 centigrades. Okay? That's the increase of temperature. So what they ask is force created by the rod on the walls. So due to this extension is trying to extend, so as a result of that the walls are compressing this. So what they ask is these compressive forces, actually F. So I'll just use this equation. First I'll just derive that, right, because some students don't remember that in case. So F is equal to YA E divided by length, that is F. But you don't know the extension here, right? Term for extension. So what do we do? We don't know how much of an extension that would be. So for extension, we have this equation. You will learn more this in thermal physics, right? So extension is equal to what? L naught, initial length. Here the initial length is taken as simple L, right? So I'll use simple L. Alpha, linear expansivity times temperature increase. So that is extension. So I'll just use this here. Y, A, extension is L alpha delta theta divided by length. L cancels off. So the compressive force becomes Y, A, alpha delta theta. So you just have to substitute values now, right? This is the compressive force. So Y is what? 7 times 10 to the power 10. Cross section 20 times 10 to the power minus 4. Alpha 2.5 10 to the power minus 5. Delta theta. So that is 4 degrees, right? From 30 to 34. So that is 4 degrees. Right? Just choose the order of calculation, right? Then the calculation also gets easier. Don't just keep calculating at once. Calculate the easiest ones first. So 2.5 times 4 is 10, right? 10. 10 times 10 to the power minus 5. When you multiply this by 10, this becomes minus 4. So we have 10 to the power minus 4 from all these. This 10 to the power minus 4, 10 to the power minus 8. Then 10 to the power 10 minus 8, 10 to the power 2. Okay. 7 times 20. That is 140. Times 100. 2 zeros. So the force cost is 14,000 newtons. Do we have an answer for that? Yeah, 14,000 newton means 1.4 times 10 to the power 4 newton, right? 1.4 times 10 to the power 4 newton. So the answer should be third one. Okay. So these forces are like very large forces, right? 10 to the power. So if I just recall you something like, you have seen in railways there's a gap between two rails. That's the reason, right? Because when temperature increases, these rails extends, right? Expand actually. So if there was no gap, what happens when they expand? Rail would bend like this. Okay. Right, take it down. And those who did the question, try 55, next question. Right, 55th question. A metal rod with cross-sectional area A is fixed between two concrete holders as shown by the image. Force exerted by each hole on the rod when temperature increased by delta T. So temperature increases delta T. This is similar to the first question, right? So again they ask expression for capital F. So we know capital F is what? Y A E divided by L. Y A divided by L. Actually they say that Young's modulus is, they have used capital E. This extension as I discussed before, that is the linear expansion, right, due to temperature increase. So that is length alpha delta T. So L cancels off, so this becomes EA alpha delta T. So this is the compressive force caused due to increase of temperature. EA alpha delta T. So the answer should be first one, right? First one. Right. So from this part, elasticity. So all the questions I'm going to discuss from the TUT. This is all the questions I'm going to discuss from the TUT. Now you can do other questions as well from even the past papers and the remaining questions on the TUT, right? This lesson, this properties of matter, and this part is elasticity. Elasticity has a practical. Okay, practical. You have like two metal wires, using two metal wires and a vernier caliper and load. You do a practical, right? So that practical, there's a separate video on that practical in my YouTube channel. I'll post the link on that practical as well, then you can refer that practical from that video. Okay, then this unit is completed. In the future, I'll be posting on the YouTube channel, I'll be posting exam questions as well on this lesson, right? Then so this is one part of properties of matter. Further, there are two parts. One is viscosity, other one is surface tension. Those two parts are also is very important, right? So you would get a essay questions from one of those three. Okay, so it is going to be very advantageous. This is when you complete this earlier. So I'll notice you the dates and all that when you, in order to continue other two parts of this unit. Okay, I think we have successfully, not think, actually we did successfully completed elasticity. All the theories were discussed, all the questions types were discussed, and you are good to go, right? Great.